Okay, think about this for a second. How do you measure something you can't even see? Something so incredibly fundamental that it literally makes up electricity itself? Well, that was the enormous challenge facing physicists about a century ago. Today, we are diving into the absolutely ingenious and, kind of controversial experiment that was designed to catch a single electron.
You see, back in 1909, long before we had iPhones or anything like that, scientists were stuck on a really basic question. Is electricity like water, a smooth, continuous fluid that you can divide forever? Or is it more like sand, made up of countless tiny identical grains? This wasn't just some academic curiosity. The answer was going to change physics as we know it.
So you basically had two big ideas fighting it out. On one hand, you had the continuous fluid theory, which actually explained a lot about how circuits and magnets worked. But then on the other hand, experiments with things like cathode rays, the kind J.J. Thomson was working on, strongly suggested there were these tiny negatively charged things he called corpuscles. We now call them electrons. The big problem was, no one had ever managed to grab just one and figure out its charge.
And this is where Robert Millikan and his graduate student Harvey Fletcher step onto the scene. Back in 1909 at the University of Chicago, they cooked up an experiment that was, at its heart, just beautiful in its simplicity. They weren't just going to find an electron, they were going to put it on a scale, electrically speaking.
The concept here is just brilliant. Imagine you have a tiny balloon and you're trying to make it hover perfectly still in midair using only the upward push of a fan. That's pretty much what they set out to do, but on a microscopic scale with a drop of oil. The idea was, if they could perfectly balance the downward pull of gravity with an upward push from an electric field, they could calculate the exact electric charge sitting on that one tiny drop.
So what did this thing actually look like? Well, the setup itself was surprisingly simple. You've got two metal plates, one right above the other. You hook them up to a power source to create a nice, uniform electric field between them. Then, you take an atomizer, kind of like an old-fashioned perfume bottle, and spray a fine mist of oil into the chamber. As they're created, some of those little drops pick up a bit of static charge. Then all you need is a microscope to sit back and watch the show.
Okay, so their method was like this elegant little four-step dance. First, with the electric field turned off, they'd watch one single oil drop fall, just pulled down by gravity. They'd time it very carefully to figure out its mass. Then, step 2, flip the switch. Now the electric field is pushing up. Step 3, and this is the really cool part, they would fine-tune that field, watching through the microscope as the droplets slowed down, stopped in midair, or even started to rise back up. And then step 4 was just do it again and again. And as they did this, with drop after drop, an absolutely stunning pattern started to show up.
After spending countless hours squinting through that microscope, timing these tiny falling and rising specks of oil, Millikan and Fletcher finally had their answer. And it was a discovery that would absolutely rock the world of science.
This was the magic number. What they found was incredible. The charge on every single oil drop they measured was always a whole number multiple of this fundamental value. It was never half of this number, or 1.25 times this number, always 1 times, or 2 times, or 3 times this value. This was the smoking gun. Electricity wasn't a fluid after all. It came in discrete identical packets, and this was the charge of a single one. And just look at how ridiculously close he got. His measurement from back in 1913 is only off by about 0.5% compared to the super precise value we use today. I mean, for the kind of equipment they had back then, that level of accuracy is just mind-blowing. And so, for this absolutely monumental achievement, for proving that charge comes in packets, and for measuring that packet so precisely, Robert Millikan received the ultimate prize in science, the Nobel Prize. But, as you often find with these great stories, the official version isn't always the whole story. So, this is where the nice, clean story gets a little bit, messy. Because behind the Nobel Prize and that celebrated number, there are some pretty serious questions about how the experiment was run and who really deserved the credit. The legacy of the oil drop experiment is really clouded by 2 main controversies. The first is about authorship and credit. The second one, which is arguably more serious from a scientific point of view, is about the data itself. So let's break them both down. First up, the credit. Harvey Fletcher, the grad student on the project, later claimed that he had done a huge amount of the foundational work. According to Fletcher, Millikan essentially gave him an ultimatum. You can be a co-author on this famous oil drop paper, or you can have sole authorship on a different, much less important part of the research for your PhD. Fletcher chose his PhD.
The second controversy, though, is even more troubling.
Decades later, in the 1970s, a historian named Gerald Holton got a look at Millikan's actual lab notebooks, and he found something pretty suspicious. Millikan had recorded data for way more oil drops than he ever included in his final Nobel-winning paper. This, of course, raised a very serious accusation of cherry-picking, basically only publishing the data that made his theory look good.
Now, to be fair, there is a defense here. Other people, like the physicist David Goodstein, have argued that Millikan was actually being upfront about this in his paper. He said he only used the data from drops that had a complete series of observations. And if you look at his notes, the discarded measurements often had comments about problems, like maybe the equipment was acting up. So the big question remains, was he just throwing out bad data, which is good science, or was he throwing out inconvenient data? And that's still debated today.
But, regardless of where you land on the controversies, the full story of the oil drop experiment teaches us a powerful lesson. Not just about physics, but about the very human psychology of how science gets done.
It's really a perfect case study in something called confirmation bias. It's this natural, human tendency we all have to look for and pay more attention to information that confirms what we already believe to be true. And you can imagine, once a number is published by a famous Nobel laureate, it becomes very, very hard for anyone to challenge it.
The legendary physicist Richard Feynman pointed this out so brilliantly. He said that if you look at the experiments that came after Millikan, the measured value of the electron's charge didn't just suddenly jump to the more accurate, slightly higher number. No, instead, it slowly crept up over years and years. And this timeline just shows it perfectly. For years after Millikan, other scientists would do their own experiments. If they got a result that was way higher than Millikan's famous number, they'd probably thought, oh, I must have made a mistake, and they'd check their equipment. But if they got a number that was just a little bit higher, close to his, they'd think, great, and publish it. That's confirmation bias in action, and it literally slowed down scientific progress.
So the big takeaway here is that science isn't this clean, perfect march straight to the truth. It's done by people with all of our human flaws, our ambitions, and our biases. But, and this is the beautiful part, the scientific method is designed to be self-correcting. Over time, with more experiments and more open debate, the truth does eventually win out. It just might take a while.
Which really leaves us with one final, big question to think about. Does knowing about the controversy, the authorship dispute, the possible cherry-picking, does that take away from the brilliance of the original experiment? Or does it just serve as a powerful reminder that even our greatest scientific leaps are, at their core, profoundly and fascinatingly human endeavors?